In this video, I'm going to talk about and probabilities. Just a quick note, and probabilities require that you already understand conditional probabilities. So if you haven't already watched that video, I suggest taking a look at it. So our first example here is we're flipping two coins and we want to find the probability that both are heads. Now there's a couple different ways that you could do this. You could just write out the sample space and compute it that way, and we've seen some examples like that in the past. But we can also think of this as an and probability by saying the probability that both are heads is the same as the probability that the first coin is heads and the second coin is heads. So we're thinking of these as two different events that both must happen. So this is in comparison to the or probabilities that we looked at before. So the way we compute and probabilities, in this case, we could just look at the probability that the first is heads, and then we're going to multiply by the probability that the second is heads. So that's something to keep in mind. Every time you see an and probability, it's going to end up being some sort of multiplication. So if we're thinking of these as two separate events, the probability that our coin is heads is 1/2. And then same for the second one, so we get 1/2 times 1/2. Remember, if it's been a while since you multiplied fractions, right? You multiply the tops together, that would be 1 times 1. Multiply the bottoms together, you get 1/4 here. And this is the same as if we had just listed out the sample space. There's 4 different possibilities, and the probability that both heads is 1 out of those 4. Here's one that's a little bit more interesting than just coins. So based on recent studies, it's determined that among men, the lifetime risk of developing cancer is about 43.92%. And this is for all cancers put together. So if we choose 3 men at random, what's the probability that they will all remain cancer-free? And the reason this is an and probability is, again, we're going to think of this as the first man is cancer-free and the second man is cancer-free and the third is cancer-free. So we're going to set this up as an and probability. And since this is an and probability, even though we have 3, we're going to do it the same way. We first treat the first person as a separate event. And then since we also want the second person to be cancer-free, we're going to do multiplication, right, times this next probability, and then again times the third. And of course you don't have to write them all out like this. I'm just trying to show what we're computing here. So we first need the probability that the first person we choose is cancer-free. Now notice that the probability we were given is actually the probability that they do get cancer. So the probability that they don't have cancer, we're thinking of this as a complement, right? If they don't get cancer, that means not cancer. So remember, in our complements, we do 1 minus, in this case, the probability of having cancer. So this tells us that the probability of having cancer is 0.5608, or 56% approximately. So the probability that our first person is cancer-free is 0.5608. The probability that the second is cancer-free is the same, and same for the third. Now you could just multiply these out since there's only 3, but when you get more trials involved, remember that this thing times itself 3 times. This is the same thing as just raising this number to the third. So optimize your calculations here and just do a cube power here. If we round to 4 decimal places again, this comes out to 0.1764. So that's about 17 or 18% that 3 people that we choose at random would not have cancer anytime during their lives. Just as a little note, what if these 3 people are you and your 2 friends? This gets at the important piece that these are 3 random people. If you're looking at you and your 2 friends, you're probably going to share some characteristics in terms of lifestyle, in terms of age, in terms of, maybe things that you eat, things like that, that could affect your cancer rates. So this really only works for randomly selected people, because certain people will have much higher rates of cancer, certain people would have much lower rates of cancer. So be careful with those randomly selected versus maybe some selections that aren't so random. The next thing that we need to get at is, what if these events aren't independent? In the past two examples, the two events or three events were independent, as in the first person that we choose, if they had cancer or not, does not affect whether the next person that we choose would have cancer. In many cases, this is not the case. So when we don't have independent events, like if you're dealt two playing cards, so again, imagine you're playing blackjack or something like that, and we want to find the probability that you're dealt two aces. Well, as we discussed in the conditional probability video, the cards that are dealt first affect the probability of what's going to come out next. For a easy way to think about that, imagine that 4 aces had already been dealt. Well, the probability of getting another ace would then be 0 because there just aren't any left. So in this case, we're looking at the probability that the first card is an ace and the second card is an ace. We're still going to do this as multiplication. So we have the probability the first is an ace times, normally we would just say the probability that the second card is an ace. But because this is conditional, or because these are not independent, we have to say the probability second card is an ace given that we already know the first card came out an ace. So you can think of this as sort of a two-step process. First, we find the probability that the first card comes out an ace, and then assuming that that has already happened, we do the next probability. So this is still multiplication. We just have to take into account the conditions. So the probability that the first card drawn is an ace would be, well, there's 4 aces out of a total of 52 cards, so 4 out of 52. And then the probability that the second card is an ace, given that the first was an ace, if we've already been dealt an ace, that means there's only 3 remaining out of now 51 cards. So we can multiply these together and get our answer. So this tells us there's less than 1% chance of getting 2 aces in a row this way. So just to summarize here, when you have the probability of two events both happening, or an AND probability of A and B, this is going to be the probability of A, or the probability of the first event, and it doesn't really matter which one comes first, times, we're doing that multiplication, the probability of the other event given that the first event has already happened. Now, if these events are independent, then that means when we go to do the probability of B given A, the A part doesn't really matter, and so we would end up just getting the probability of B. So for independent events like we saw at the beginning of the video, this is all we have to do. But just keep in mind that whatever that first event is, if it affects the probability of the second, we have to take that into consideration. Going along with this, this is pretty important when we're talking about choosing samples, so make sure you watch the next video about independence and sampling. Okay, to finish up, we have a problem for you to try. Go ahead and read this through, figure out how to compute this AND probability, and I'll see you next time.